Okay, hello, welcome everybody. My name is Amanda Hanford and I am the CAV group leader of the Acoustic Materials and Metamaterials group. So I'm here today to kind of give you a brief overview of some of the activities that are going on in our group around Penn State, but then I'm going to hand it over to my colleagues to kind of give an introduction to the work that they're doing here at Penn State. We have two new professors in the area of acoustic materials and metamaterials, and I can't wait to introduce you to the work that they're doing. Okay, so I do have a couple of updates that I wanted to share with you. So I'm bringing up my screen here. Okay. All right. So this is just a general overview of the research areas that our group is involved in. Certainly we're involved in any kind of acoustic material related project. So that can range from material characterization using acoustics, novel manufacturing techniques for acoustic materials. We're doing we've been doing some interesting things on, some non-traditional metamaterial applications such as cloaking. We do inverse design, active metamaterials, and then using novel materials for some kind of sound and vibration control as well. So these are just the broad categories of the kind of work that is involved here in our CAV group. So welcome Dr. Harne and Dr. Yun Jing to Penn State. They're joining us here today. We have a large growing list of membership in both the faculty and students. And for those of you who are watching, please let me know if you want to be involved in this group, and your name's not listed here. So please reach out to me if you want to get involved. But yeah, we've got a lot of really great people involved in this group, and again, welcome to our new members. So I went through and just kind of pulled, this is a select group of publications and papers that were kind of put together by some of our faculty and students. This is not an all-inclusive list, but I pulled out some materials and acoustic metamaterials papers that are involved in, that our faculty and students are involved in. And so thank you for all of your hard work getting papers out into the literature. Also want to acknowledge one of the students was given an award for best paper at an international conference, and so that was really exciting. Of course, that was all before COVID, but hopefully we'll still be able to have exciting news like that in years to come. So yeah, so just a general update there on our papers and presentations. I kind of like to show this pretty much every time, but I wanted to make sure that we kind of all started on the same front when we're talking about acoustic metamaterials. So the idea here is that we are looking at a small scale features that, when depending on the size of your system and the size of your acoustic wavelength, you end up with some kind of homogenized system, right? So on the left here, we have this homogenized material. And when it's interacting with our acoustics, it has some kind of homogenized material property. But really, what a metamaterial is doing is looking at these smaller scale features, here on the right. And these two materials can be this to the acoustician. Those two materials can be the same if it's interacting with acoustics in the same way. So what we're trying to do when we're working in metamaterials is really look at what's happening at the small scale and see if we can kind of figure out what's happening at that small scale in order to homogenize our material and do some interesting things with the acoustics as it interacts. So I just wanted to make sure that we're all kind of on the same page. You'll probably see versions of this slide in future presentations by my colleagues. But this is kind of the general definition of a metamaterial, and so we're going to use this these small scale features to do interesting things with acoustics. One thing that we've done to kind of characterize these metamaterials, and one of the examples that I'm going to show today is how do we characterize these metamaterials, and looking at the small scale versus being able to extract material properties of interest. So we're interested in metamaterials underwater in this example. And so I'm going to explain a little bit about how we've actually done some testing to extract metamaterial material properties in an underwater environment, which poses an interesting challenge. So the goal here was to determine the trade-off between a couple different measurement techniques so that we could extract these homogenized material properties. So I have two examples here of being able to test a metamaterial. And so this top example is a submerged sample in a reverberant water tank. And then on the bottom here, we have an acoustic impedance tube with your material sample there in the middle, and then you have a series of sensors. So you can use the impedance tube to kind of help calculate your material properties of interest. So I'm just going to show kind of very broad overview of like the pros and cons of these two techniques and where the limitations are for a metamaterial submerged in underwater. So if we look at kind of that small scale feature of a metamaterial, we're going to break it down into a unit cell. And this unit cell it's not a super exotic unit cell, but all we have really is a solid inclusion embedded in a fluid. Okay, so our solid inclusion is made out of stainless steel, and we have water as our background fluid. And so this is what our unit cell looks like. And you can play around with certain things like the width and the length and all the geometric parameters to kind of change the effective material properties. And we can look at this in different dimensions if we want to, or sorry, different directions if we want to evaluate things like anisotropy and all those sorts of things. So we can, you know, if this is what our unit cell looks like and we want to homogenize this, we can get some effective material properties. And we did some calculations using some finite elements as well as some semi-analytical models to evaluate what the effective material properties would look like as a function of frequency. So this is just a simple calculated example of what we expect the effective material properties of this unit cell to be once we look at it in a bulk sense. So you can see we have effective densities and effective bulk modulus in different directions that are plotted here as a function of frequency. And these are predicted. So then we put it into the water tank, and we have our sample here is on the left, and we have a hydrophone sitting in front of it. And then we have an acoustic sound source up here providing acoustic energy. So here's our source, and here's our receiver, and here's our material. So the way that we did this is, you know, we had our sound source over here. We have acoustic propagation through the water, interfacing with our material sample. And then these black boxes were measurement planes. So we took a measurement, a receiver hydrophone, and took the measurements in front of the panel and in back of the panel to get reflection and transmission through this material. And we did that at all these single points. Okay, so that's one way we can get to some effective material properties. So the issues with this setup is we have some frequency limitations of this problem. At the high frequency, we're limited by our source directivity, as well as, you know, if our frequency gets too high, we no longer have an effective material. It's no longer homogenized. So we have to be careful at the high frequency. And at low frequency, we have other issues. Our tank size becomes a problem. You could end up with reflections off of the sidewalls or off of the surface, and that could create some issues at low frequency. So we do have some limitations here. So kind of on the other extreme, when we looked at our impedance tube, here's just a picture of our water-filled impedance tube in the laboratory. So there are frequency limitations of this setup too, right? Because we have issues regarding the size of our impedance tube and frequency cutoff and cut on. And so the high frequency, we're limited by the size of our impedance tube. And at low frequencies, we are dealing with things like how much source power we have. And then actually, I didn't really show this, but we'll have sensors. Well, here, let's go back here. So here we have these hydrophone sensors kind of right here in the tube wall. And placement of these sensors is going to also dictate what happens at low frequency. Okay, so I'm not going to show any results. I just kind of wanted to show some trade-off studies here. So, you know, we had a series of trade-offs using these two different measurement techniques. I already mentioned the frequency limitations, but additionally, there are other trade-offs that we ran into, right? Since we're in an underwater environment, bubbles are an issue in either case. But we have other things that we need to worry about. It's more relevant underwater than it is in air, such as shear waves, exciting or shear waves of our structure, of our material, sorry, and you know, differences in sample sizes. So I kind of wanted to just briefly mention all of this. We have some preliminary results in works getting ready for publication, but it was just a nice brief update on a couple of different techniques that we do to do this material characterization for underwater environments. Okay, so with that, I'm going to back away, and I'm going to now introduce Dr. Ryan Harne, so he can give us a brief overview of the work that his group is doing at Penn State, and so welcome, Ryan.
Zoom folly, almost left myself muted. Thank you, Amanda, for the introduction, and it's great to be a part of the center now, and welcome everyone to the workshop. Thanks for attending this session on acoustic metamaterials. As Amanda said, my name is Professor Ryan Harne. The laboratory that I initially began at Ohio State University is now transitioned to Penn State. And we call ourselves the Laboratory of Sound and Vibration Research. And I think that you'll find through this quick introduction that I'll give of our lab's activities that we do cover a much broader range of research and scholarly work outside of just sound and vibration. So we would, let me make sure I'm on my presentation mode here. We would say that in our lab's research, we investigate research topics and problems of society that pertain to fields of vibrations, acoustics, mechanics, manufacturing, as well as smart materials. And the research activities in our lab that are kind of core to our day-to-day programs constitute research programs on smart and soft and smart electronic material systems, active acoustic and mechanical metamaterials, origami-inspired medical transducers, as well as other wave propagation concepts. And finally, modeling tools for multi-stable structures. So the following slides will give a quick snapshot, mostly visually, of what activities have been undertaken so far and where we're going in these areas. So firstly, in our research programs on smart and soft electronic material systems, we start with an idea, or I would say a vision, of creating fully autonomous soft engineered matter, very similar to effectively an engineered equivalent of a biological system, something that can think, something that has a fuel resource, something that has sensory capability, actuation capability, and is all constituted within some frame, a body or a shape of some sort. And this is a very big vision, and it involves many, many physics, as well as many length scales. And what we're looking at in this area of research in our lab is constructing the decision-making ability that's concurrent with sensors and actuators. So in our research on soft and smart electronic material systems, we're creating conductive, flexible electronic networks in soft matter. So this is an example of a silver trace that's applied to a TPU or thermoplastic polyurethane substrate, the blue object. So the silver trace is a combination of silver and TPU. And we see that based on the design of this material, which genuinely, adopts some of these metamaterial capabilities or definitions, the material will open and shut an electronic circuit according to the mechanical stress, effectively giving you a sensed signal. And in fact, this is a digital signal. It's not a pure mechanical behavior. And we've studied the behavior of this type of trace for a wide variety of systems to understand both the mechanical behavior as well as the electrical behavior. And through all of these efforts, we're creating this foundation of understanding how to use flexible electronic materials for sensory as well as decision-making capability. So some of the digital switches that we're investigating so far involve literal logic gates placed inside of constructed on the basis of the combination of the silver TPU network as well as the geometry of the substrate. So, and these videos just show some demonstrations of electronic switches that can be considered as constituents or unit cells that we build up into smarter, full-featured electronic functions. So in summary, what we're doing in this research activity in our lab is giving mechanical metamaterials or material systems the means to think about the stresses that are applied to them. So in other words, instead of having silicon microprocessors perform all of this decision-making functionality, the materials themselves actually think about what's going on, then pass logical sequences and binary signals to adjacent actuator controllers, what have you, control systems that could ultimately drive our responses. In our lab's research on active acoustic and mechanical metamaterials, we studied a wide variety of solid, cellular, composite, poroelastic media, and similar to Amanda's team, we're investigating how both harmonic as well as transient loads acting on these materials give rise to unique behavior. We often do mesoscale, handheld tabletop demonstrations of our applications, and we're investigating presently how to control this behavior through pneumatic, fluidic, and other pressurized means with very strategic low input, low output configurations, especially since a large number of cells that you see or pores that you see in this mechanical metamaterial here might otherwise suggest a large number of individual units to operate on. We study a lot of loads applied to these materials. More recently, we're giving great attention to shock and other transient forces. This necessitates high-speed videography. So we have full high-speed recording capabilities in our lab, up to 1 million frames per second. If you're a novel or a novice photographer or a beginner photographer like me, or maybe you'll have a little bit more experience, you would understand that that requires a lot of light to come into the aperture. So when we perform high-speed videography, we have to dump and saturate the object with an extreme amounts of light. These are very short tests, otherwise the light heats up the object. There's so much light. So yeah, we oftentimes use high-speed videography so we can then use digital image correlation to track the motion of the sample before and during applied loads. So then, in this case, we can map out displacement, strain fields, strain components, and so on. It's a pretty involved and impressive process, but leads to some very insightful conclusions, in this case, about how applied force passes asymmetrically through this polar elastic material. So, in the next area of research in our lab, we are inspired by origami, reconfigurable structures. A lot of our attention is devoted to the development of medical transducers that use high-intensity focused ultrasound to thermally ablate cancers that are in the body. The photo at the left shows a commercial probe created by Sonicare Medical, which is located in Raleigh, North Carolina. It's the nation's largest manufacturer and developer of HIFU-based transducers, specifically in this case for prostate cancer treatment. has a 100% success rate to use HIFU for prostate cancer treatment. And this is a probe that is inserted into the rectum, blasts out the cancer, and then is removed. That hemispherical shape that the transducer adopts helps it to focus at the cancer itself with high precision. On the other hand, this probe is much too large to tackle some of the other cancers in the body, for instance, liver cancer, other cancers within the torso, as well as in the chest. So our vision is to use the principles of origami, where we realize this focused sound field by curvilinear and hemispherical transducer shapes, but we're able to pass that transducer object to the point of care in the deployed state realized by the folding sequence of this origami-inspired tessellation. So this is a research activity that's actually carried out in conjunction with support from Sonicare themselves. We're very interested in this concept since the success rate of HIFU for prostate cancer treatment is extraordinarily amazing. They'd like to see how we can transport HIFU practices to a much greater range of cancer treatment deep in the body. So this concept leads to easily miniaturized and manufactured deployable HIFU transducers that we're currently studying today. This research is highly analytical. It involves detailed modeling of the wave fields that would be created by this reconfiguration of acoustic transducers. And we ultimately design and study small laboratory scale samples that perform this type of wave focusing functionality. We're also extending this to other sorts of acoustic communication. Specifically, I say with a great emphasis, what's not shown on this slide are research activities that are going on now for reconfigurable hydrophone arrays underwater. We should have a paper coming out in the Journal of the Acoustical Society of America right now. It's a 2020 JASA work. I'm glad to share that with anyone who's interested on reconfigurable hydrophone arrays that perform just as well as multi-spiral arrays, but are fully foldable into an extremely compact state. And we have great experimental validation of those exciting results. So I'm glad to share that result with, or those outcomes with anyone who would like to contact me later. And the last year of research in our lab stems a lot from my original PhD and postdoc training, and that's in analytical nonlinear dynamics. A while ago, we started building up analytical tool set for multi-stable structures. What do we mean by multi-stable structures? These are systems that adopt a variety of statically stable equilibria that can be transitioned among through external perturbations or the use of applied fields internally. And we see this in a wide variety of contexts. For instance, in biological systems like skeletal muscle, the nanoscale cross bridges undergo a state conformation change to pull on muscle fiber and thus lengthen, contract it, and creating force for the body. It's a multi-stable structure that's been well known and studied for years with computational methods, that is. In hypersonics, the air vehicles are subjected to extreme aerothermal loads that oftentimes cause flutter, snap-through buckling, and other catastrophic events. And currently, likewise, studied through computational methods. And finally, another area that we study with our tools in the lab is on vibration energy harvesting systems. Not just the structures, but also the packaged electronics, which constitute power conditioning circuitry, control approaches, and as well as real-time optimization. These three areas have long been studied computationally. What our lab brings to the table are analytical tools grounded in applied math that lead to direct solutions for transient, steady state, and stochastic behavior that would apply to this and more types of engineering systems. We continue to find new ways to apply these mathematical tools, which demonstrates the robustness and versatility, as well as the grounded physical principles on which this approach has been established. But more than just research, being a part of our lab, the Laboratory of Sound and Vibration Research, is a commitment to a team. I'm devoted to my students. I'm devoted to their current academic and graduate efforts, as well as to their future professional trajectories. So from day one of joining our Laboratory of Sound and Vibration Research team, our students are put on a track for early career development. And that involves getting active in conferences and poster presentations, to publishing the discoveries of their research, to applying to awards that they rightfully deserve and are great candidates for. So I'm very active from day one to their graduation and beyond. So I'm very keen on that. So we're really dedicated to our discovery and our professional development. We're equally as dedicated to the community of our team. So whether that's working with local school groups on project activities to expose students to acoustics and vibrations early on, or enjoying the environment, this is of our community. And this is our team going to the Columbus Zoo a year ago, giving a high five to an orangutan. Or lastly, just getting together and enjoying our company. I'm a great proponent of a strong community that leads to excited researchers that are pleased to be a part of this team and then do amazing things for our lab. So thank you, Amanda, for your time. Thank you, everyone, for who's attended this talk. And yeah, feel free to get in touch with me whenever you'd like. Thanks.
Thanks, Ryan. That was really great. I meant to mention earlier on that it is the intention of the CAV to host both of our guest speakers today in a more detailed CAV lunchtime seminar. So we are looking to get those scheduled very soon. So we look forward to hearing more about that at a future date. But thank you. And so now I'd like to introduce Dr. Yoon Jing, who's also going to give us an overview of his experience and what's going on in his lab here at Penn State. Thank you. I think you are still muted.
Yes, I was looking for the button.
Okay, very good. All right, go ahead.
Okay, thank you, Amanda, for the introduction. So my name is Yoon Jing, and I joined Penn State, the graduate program in acoustics this January. Before that, I spent about 8 years at North Carolina State University, the mechanical and aerospace engineering. I'm very happy to be here, and this is my first experience attending this this workshop, virtual workshop. So very excited about it. So today I would like to talk about two of our recent works from my students. So our lab is very interested in designing acoustic and elastic metamaterials for controlling mechanical waves. So the two topics that I'm going to talk about today, the first one is acoustic metamaterials. So specifically, I want to talk about how we design a metamaterial to absorb low frequency sounds. And the second topic is where we design a metamaterial, elastic metamaterial, where we control elastic waves or vibration. So let's talk about the motivation of why do we want to control low frequency sound. And particularly in the room acoustics, this is a largely unsolved problem. We are looking at very low, extremely low frequency sound, the sound below 100 hertz. So if you think about room acoustics, you have normal modes that are manifested as high frequency region at the corner of the room. So you want to be able to absorb those normal mode frequency sounds to be able to have a flat response of the room. So what you see here in this picture is a corner bass trap people use to absorb low frequency sound, but this kind of material is actually very ineffective, does not actually absorb a lot of energy at extremely low frequency, and also it's very bulky. So this is something we would like to address using metamaterial. As you can see, our design looks like this one here. This is basically a panel where we have, it's a repetition of a periodic arrangement of unicell, what we call here. The unicell looks like this. You have a perforated panel, you have 4 different perforations with different sizes, and they have 4 different necks go into cavities. The cavities are identical for cavities. So this is our acoustic metamaterial panel, and we'll put the panel into this impedance tube for measurement. So the underlying mechanism to put this simple, in simple words, is based on optimally coupled acoustic resonators. So here we have the blue curves is the measurement, and the red one is the theoretical result, and the black circles are from numerical modeling. We use commas over here. As you can see, we have a very nice agreement between the theory and modeling. The measurement, we have some deviation here, there. We think the reason is because we are neglecting the acoustic structure interaction in our modeling and theoretical model, which is not really negligible in such low frequency region. But overall, the agreement is very nice, I think. And we had to look at the thickness of the panel. It's 15.4 centimeters. It's still pretty large, but if you think about the wavelengths at 50 hertz, it's 50 hertz like like 3 meters long, something like that. Actually, more than that, yeah. But so this thickness panel is 140. Almost 1/45 of the wavelengths at 50 hertz. So it's relatively thin, I would say. We can also look at oblique angle of sound absorption at other oblique angles. We cannot do that measurements. So what you see here, this is numerical modeling and theoretical analysis. You have 10 degrees, 30 degrees, 50 degrees, 70 degrees, and this is the average sound absorption over all the frequency. So as you can see, with our sound absorbing panels works up to a frequency of 60 degree, which is pretty nice. So I think that's sufficient for room acoustics. So just some quick concluding remarks. The same design strategy can be easily adopted for designing sound absorbing panels for other frequency ranges. So right now we're looking at very low frequency, is the 1/3 octave band. We have achieved the 1/3 octave band for sound absorption. We are also interested in grazing angle sound absorption because in some applications, the sound incidence is not the normal incidence, but it's rather the perpendicular, the 90 degrees angle. And also we are thinking about how we can modify the design so that it can be applied to underwater sound absorption, which is another interesting application. Okay, so moving on to Elastomer Materials, just very quick background. We are specifically talking about designing engineered mechanical materials to stop vibration. This has been done by many groups. The problem is that these materials from previous works very heavy and bulky, so they are not really practical for real-world applications. And on the other hand, there's also another research topics. A lot of people are getting into this area, which is a micro-lattice-based metamaterial, which you can see in these pictures. Very fancy structures. They give you a lot of very interesting functionalities, such as they're very lightweight. They're, at the same time, they are very strong, very stiff. So that's an interesting topic too. So we're thinking about combining these two. So can we design a micro-lattice metamaterials that can stop vibration? So this is our design. This is a specific type of metamaterial called auxilic metamaterial. Basically, this kind of material has a negative Poisson ratio. Conventional materials have positive Poisson ratio. So we are using a particular material to design this. Is HDDA. You can find the properties here. And this is our unit cell. We have the several things can be tuned. The angle here, periodicity, and that is constant A. And we calculate the band gap, the band structure. So basically, what you need to know is that this shaded area is the area where the vibration cannot pass through. We normalize the frequency, so you cannot really tell what the actual frequency, physical frequency range here, but it's a broad band frequency range. We look at this mode here. This mode is very interesting. That actually tells you why this can stop vibrations. If I go to the next one here, if you look at this mode, is vibrations like what they call trampoline mode. And this mode is known to be able to enhance to increase the band gap of local resonance. So we also look at how this metamaterial compare, how does this metamaterial compare with existing designs. We found that this is really striking to us. Our structure is really, really lightweight. This is 0.03 for 1 gram per centimeter square. If you think about, you look at other materials that are far heavier than our design. And of course, and also on the other hand, at the same time, our band gap are also lower. So in other words, we have, if we look at the same size of the material, we can stop a much lower frequency vibration, which is very important. And fabrication, we collaborated with a professor from UCLA, Professor Jing. He's an expert on this large area projection microstereolithography. And he helped us to create 3 samples in different orientations. And we took it to the Naval Research Lab at Washington, DC to measure these, the transmission. And this is a measurement, and this is the simulation. You can see within the band gap, we did observe a transmission reduction of the vibration. Here we look at, student made this animation showing that if you put a shaker, if you apply a vibration on the bottom of the sample, the vibration does not actually pass to the top of the sample, so it gets stopped. So just to conclude, some perspectives on this work, we would like to continue working in this area, and specifically we want to look at how do we add additional functionality to this metamaterial. For example, how can we make this, some absorbing materials? Can we also incorporate hierarchy structures into this metamaterial to enhance the functionality? And also, can we make this metamaterial reconfigurable? So right now, once you fabricate this, it's fixed, right? But what if we want to tune the band gap? Can we make this reconfigurable? So that's it. I think that's what I want to talk about today. And if you have any questions, you can send me an email. So let me start sharing.
Wonderful. Thank you. That was really great. Nice overview and a lot of different different applications and and a lot of different approaches there. So this was fantastic. So I want to just thank you both for participating in our group's overview today. And as I mentioned earlier, I will plan on scheduling some follow-up seminars. So we look forward to hearing from you both and/or your students in upcoming time. So thank you again, and I hope to all of you workshop participants that you've enjoyed this presentation, and let us know how we can help. So thank you very much, and have a great day.